did the basic definition, and then we did 2 examples, I guess, 1 or 2 examples. Right, and at the end of the class I gave you some homework, 3 problems to solve. And yeah, all are kind of straightforward. Say for example this second problem, yeah, first problem you could have verified this. Just apply the Fourier, no sorry, not Fourier, just apply the Laplace transform definition and you will see whether it is correct or not. Yeah, and before discussing 2 and 3, let me start with what can we so what we had was, we have done this e power minus at u of t, and its Laplace transform came out to be 1 by s plus a real part of s is greater than minus a. So this is the region of convergence, right? So the Laplace transform exists only when real part of s is greater than minus a for this signal, right? Yeah. So just apply this here. So in the second homework problem, what I asked you was, find Laplace transform of u of t from Laplace transform of e power minus at u of t. Okay. So now if we want to find Laplace transform of u of t, this I can write it as Laplace transform of e power 0t, e power minus 0t u of t. That will be 1 by s plus 0. In place of a I put 0, and its convergence will be real part of s is greater than 0, because simply I put a equal to 0. So Laplace transform of u of t is nothing but 1 by s. Laplace transform of u of t is nothing but 1 by s part of s is greater than 0. Okay, and another notation for Laplace transform is, we will write x of t here, and on the arrow mark we will put lt here. Lt stands for Laplace transform, and then here we write x of s. So this is the time domain signal, this is the s domain signal, this is the original signal, and this is its Laplace transform, and both are connected through Laplace transform because it's a Laplace transform pair, right? And then for question 3, what we had was 3. Okay, let me see this. 3 e power minus 2t ut, 3 e power minus 2t u of t minus 2 e power minus t u of t. Right. Yeah. Now this you can find its Laplace transform from the basic principles, like apply the Laplace transform, like integral minus infinity to plus infinity x of t e power minus s t dt. Or you can simply use this. You can use this pair here. See, when we have e power minus a t u of t, we are getting 1 by s plus a, and it's the region of convergence. So using that, I can write 3 is a scalar, and it will be 1 by s plus 2 minus 2 1 by s plus 1, right? This I'm doing it using e power minus at u of t. Its Laplace transform is 1 by s plus a till of s greater than minus a, right? Yeah. So this is the x of s. Sorry, here I should write x of s is this 3 divided by s plus 2 minus 2 divided by s plus 1. See, I advise you to verify this again through deriving Laplace transform from the basic principles. Like you can do its Laplace transform. So you can do it through 3 e power minus 2t u of t e power minus st dt minus infinity to plus infinity 2 e power minus t u of t e power minus st dt. So if you solve this also, you will get 3 by s plus 2 minus 2 by s plus 1, which is same as what we got here, and now the most important part is this will converge if real part of s is greater than minus 2, and this will converge if real part of s is greater than minus 1. You can also find this convergence, region of convergence. So ROC for this signal is real part of s greater than minus 2, and the region of convergence for this signal is real part of s is greater than minus 1. How? You can find the ROC of this signal separately, and you can find the ROC of this signal separately. Right? And then now we want ROC for this x of s. So that meaning, did we introduce you? Just a minute. I think S-plane I have introduced you, right? Whether we did the S-plane? Yeah. So this is the S-plane. Okay. So on the S-plane, so this is real part of S, this imaginary part of S, and this is all our S-plane. Say this 3 by s plus 2 will converge if in this region, if this is sigma equal to minus 2, or this is the real part of s, or real part of s equal to minus 2. So this part of the Laplace transform will converge in this region. In this region from minus 2 to infinity it will converge. So this is minus 2 to infinity. Infinity you can include. And the other thing will converge. So this part is real part of s is equal to minus 1. It will converge in this region. So for this x of s containing both the terms, containing both this 3 by s plus 2 and 2 by s plus 1 to converge. It will converge only in the region overlapping in the intersection region. So overall, right? So ROC of x of s is intersection of -2 to infinity and -1 to infinity. That is equal to -1 to infinity, right? So ROC of x of s is real part of s greater than -1. So finally what you should write, x of s is equal to 3 by s plus 2 minus 2 by s plus 1 with real part of s greater than -1. See, always, as I said in the last class, when you are mentioning the Laplace transform, always you have to state its region of convergence. Always you have to state real part of s is greater than something or less than something, or sometimes, as we will see in today's class, sometimes the region of convergence will be the entire s plane. Means it will converge everywhere on this s plane. In that case, only in that case you need not specify what is the region of convergence. No. In that case as well, you should say that this Laplace transform will converge on the entire s plane, or the ROC is entire s plane, right? So always it is important to state the region of convergence, because as we have seen, right? See what we have seen in the last class. If I have x of t, which is equal to e power minus at u of t, then say that this is x1 of t, then x1 of s means the Laplace transform of x1 of t is 1 by s plus a, and region of convergence is real part of s is greater than minus a. Then if I consider another signal, see this we did in the last class, you just go back and refer your notes. So if I consider another signal, which is x2 of t equal to minus e power minus at u of minus t, then it also has got the same Laplace transform. It also has got the same algebraic expression for its, but its region of convergence is real part of s less than minus a, right? So note that both x1 of s and x2 of s means the Laplace transform of x1 of t and the Laplace transform of x2 of t have the same algebraic expression, right? So if you just see the expression 1 by s plus a here, 1 by s plus a here, so there is no difference, right? But Laplace transform is a one-to-one mapping. It is a one-to-one mapping between time domain and s domain. So does that mean that both e power minus at u of t and minus e power minus at u of minus t both are same? No. This signal is defined only for time greater than 0. This signal is defined only for time less than 0, as you can see. So this signal will be there from time 0 to infinity. This signal will be there in the time only 0, minus infinity to 0, right? But these two are having the same algebraic expression, means 1 by s plus a, 1 by s plus a. So the distinguishing factor the distinguishing factor between x1 of s and x2 of s is their region of convergence, right? So it is essential sorry, it is essential to state the region of convergence when we state or find the Laplace transform. See, what happens is when you give only this algebraic expression and don't give the region of convergence, it's as good as you haven't done anything. It's good. It's as good as you haven't solved the problem. So some of the examiners may put simply 0 if you don't specify the region of convergence. And let me tell you, this is the common mistake students do mainly. Like here in the Laplace transform as well as in the jet transform, which we will study after this unit, both these transforms have region of convergence. So unless you state the region of convergence, you haven't solved the problem completely. So some examiners may give partial marks for finding the algebraic expression of this x1 of s or x2 of s, but unless you state the region of convergence, it means that you haven't solved the problem. So, but in Fourier transforms, you don't have this region of convergence, right? Because in Fourier transforms, the Dirichlet condition says that whether a Fourier transform exists or not. So, if you are given a signal for which Fourier transform does not exist, you will simply state that the Fourier transform for this signal does not exist, and you will find Fourier transform only if it exists. So the one main factor that is different between Fourier transforms and Laplace transforms, or Fourier transforms and jet transforms, which the jet transforms we will study later, is that in Fourier transforms you will find the Fourier transform only if it exists. So there you need not state region of convergence. Here in finding Laplace transform, you will find the Laplace transform though it exists only for certain values of s, and you state that this exists only for these values of s. So you please keep in mind that you always have to state this ROC, right? Okay. So so one more example. So we don't solve this, but I'll give you some steps so that you can complete this. So another example is, let me see. Yeah. So another example that we can do, it's also a simple example. So e power minus 2t power minus 2t ut plus of, no, sorry, there is no of, e power minus t cos 3t. E power minus t cos 3t of t. Find x of s. So find its Laplace transform. See, when here you have something different, like cos 3t you have, right? So the one you know how to find the Laplace transform of signals, this exponential signals, e power minus 2t or e power minus at in general. But so here just one thing that you have to do is express cos 3t as, how do you express, e power minus j3t plus e power plus j3t divided by 2, right? So this we can write this as e power j3t plus e power minus j3t divided by 2. And then substitute here. So now you have x of t in terms of all exponential signals. E power minus 2t ut, e power minus t, right? So here you will have it in terms of exponential signals. And find x of s. So this again I'm leaving it as a homework problem. As you can do it, it's only this substitution is required, right? And then yeah, so and then I'll give you the solution so you can verify that. X of s is equal to 2s square plus 5s plus 12 divided by s square plus 2s plus 10 multiplied by s plus 2. And region of convergence is real part of s is greater than minus 1. Right? And let me tell you, this is an example problem. So examples are taken from the book Oppenheim and Wilsky. Second edition. So I'm following for teaching Laplace transforms. I'm following the book Oppenheim and Wilsky. So you can refer to that book. That is the most referred book in general, like this Oppenheim and Wilsky. And I'm sure you will have it in your libraries. Yeah. So okay. So this you will solve it as homework problem again, and then now let's come back to the discussion. Rational Laplace transforms. Okay, so you must have observed that most of these, almost all the Laplace transforms we derived till now, like we did some three or four examples, right? So in most of them, the x of s, the Laplace transform, is in the form of a numerator polynomial in s divided by the denominator polynomial in s, right? Say for example, in the case of e power minus t u of t, what do you have? 1 by s plus a, right? And then what else we solved? Yeah. And then we had something called 3 by s plus 2 3 by s plus 2 minus 2 by s plus 1 in another example. So this we can write this as s minus 1 divided by s square plus 3s plus 2. So here x of s is 1 by s plus a form, or x of s is something like s minus 1 s square plus 3s plus 2, and here and here we have x of s is 2s square plus 5s plus 12 divided by this. So in all these things, x of s is in the form of a polynomial in S divided by another polynomial in S. So here n of s is numerator polynomial, so n of s is a polynomial in the numerator, and d of s is the polynomial in the denominator. So d of s is polynomial in S in the denominator. Right? So such Laplace transforms are called rational Laplace transforms. Like, of course, you know it's a rational function now. X of s is a rational function because it has got a numerator and it has got a denominator. Now, for such Laplace transforms, say now n of s being a polynomial in S, it will have some roots, right? So let's go to that discussion. Like, yeah, so I'm going to switch the base. Right? Hope you have noted down. Anyway, I can send you this as a PDF. I can convert this into PDF and then send. So n of s will have its roots. Roots in the sense the roots of a polynomial, right? Every polynomial will have a roots, right? A degree nth polynomial will have n roots, and n of s and d of s both will have their roots. So let's examine what happens to x of s at these roots. At the roots of d of s, okay. So yeah, now we know that it will have its roots. So in x of s, if we put s is equal to a root of n of s, then x of s becomes 0, right? See, x of s is n of s divided by d of s, and n of s has got some roots. So when I substitute s is equal to that, so this n of s becomes 0. So 0 divided by d of s, it becomes 0, right? So x of s goes to 0 when s takes the values of the roots of polynomial n of s. So those values of s are called zeros of the Laplace transform. Say again go back to this example. Say 1 by s plus a. No, not 1 by s plus a. So for simplicity, let's go back to this s minus 1 . So consider x of s minus 1 s square plus 3s plus 2. 3s plus 2. So here n of s is s minus 1. So roots of n of s are s is equal to 1. And d of s is s square plus 3s plus 2. And roots of d of s are s is equal to minus 2 and s is equal to minus 1. Right? Yeah. Now, in this x of s, so x of s at s is equal to 1, what happens? It's 0. This becomes n of s at s is equal to 1 divided by d of s at s is equal to 1. So in the numerator we have got 0. Definitely, because at s is equal to 1, the numerator is becoming 0. And 0, denominator, there may be something else, some finite quantity. That means finally it is 0. So this s is equal to 1 is a 0 of Laplace transform x of s. Because the Laplace transform is becoming 0 at those values, we call the roots of n of s are the zeros of Laplace transform x of s. Similarly, right, the roots of n of s are called the zeros of Laplace transform x of s, as x of s becomes 0. At those values of s. Similarly, what we can say, x of s at s is equal to, let's put minus 2. Minus 2 if we put, then at s is equal to minus 2 divided by d of s, s is equal to minus 2. So this will be something in the numerator, and in the denominator it will be 0. Because s is equal to minus 2 is a root of the denominator polynomial. Right? S is equal to minus 2. So we have seen that this is one root of denominator polynomial, and this is another root of denominator polynomial. So similarly, so this becomes infinity. Similarly, x of s at the value s is equal to minus 1 is also something divided by infinity. So n of s is equal to minus 1 divided by infinity, that is equal to, oh sorry, divided by 0, because, yeah, let me write this. So this is d of s is equal to minus 1, and this becomes 0, that is equal to, right. So the roots of d of s are called the poles of Laplace transform x of s. As x of s becomes infinity, at those values of s, right? So the values of s for which x of s becomes infinite are called the poles of x of s. Pole because it suddenly increases. It's like Dirac delta function. It increases. It shoots up to infinity. Right. So for a Laplace transform, we will have poles and zeros, especially for a Laplace transform when it is expressed as a rational function. As a rational function meaning some numerator polynomial divided by a denominator polynomial. The roots of the numerator polynomial are the zeros of the Laplace transform, and the roots of the denominator polynomial are the poles of the Laplace transform, right? And apart from these poles and zeros, we will also have some other poles and zeros. Like we'll discuss that shortly. But now we can nicely denote these poles and zeros on the S plane. See, we were drawing the S plane, right? So we can also denote this. So let's that is called pole zero plot, or pole zero diagram. Let us see what it is. Okay. Say again I take the example, same example. It is the simplest example. Say x of s is equal to s minus 1 divided by s square plus, what is that? S square plus 3s plus 2. 3s plus 2. So its zeros are s is equal to 1 and poles are s is equal to minus 2, s is equal to minus 1. So it's pole zero diagram. See, sometimes you will be asked only to draw the pole zero diagrams. But to draw the pole zero diagram, you have to first find the Laplace transform and then plot the pole zero diagram, right? Yeah. So there is a 0 at s is equal to 1. Say this is 1 and this is minus 1 and this is minus 2. And this is the real part, this is the imaginary part, and this is the s plane. So at s is equal to 1, we have a 0. So we'll draw a small 0 at s is equal to 1. And the poles are denoted by X marks, the cross. So so this mark denote pole and this mark denote 0. Right? So it has got two poles, one at minus 1 and the other at minus 2, and it has got a 0 at s is equal to 1. Right? Yeah. What else do we have to do with this diagram? So one more thing. Okay. Yeah. So now we can make some observations. Observation is that degree of n of s is less than degree of d of s, right? See, the degree of the numerator polynomial is 1 here, whereas the degree of the denominator polynomial is 2, right? You can see that straightforward. And then now, if s goes to infinity, right? If s goes to x of s, in the limit s goes to infinity, so what happens? In the denominator, there is s squared term. In the numerator, there is only s term. So as s goes to infinity, it becomes 0. So that means as s goes to infinity, x of s goes to 0. Or if you simply put s is equal to infinity, like as in the denominator we have a higher degree of s, x of s becomes 0. So x of s has another 0 at s is equal to infinity, right? See here, it is clearly seen that x of s has got a 0 at s is equal to 1. Like if we put simply s equal to 1 here, x of s is becoming 0, and so we have a 0 at s is equal to 1. Clear? But when we can also observe that when s goes to infinity, when s in the place of s, if you put infinity, then also x of s becomes 0, because the degree of the denominator polynomial is higher. So you have another another 0 at infinity. But generally in a pole 0 diagram, you cannot include that, because you cannot extend this line to infinity and then say that. So you have to simply state that it has got a 0 at s is equal to infinity. So if you are asked, then poles of x of s are s is equal to -2, s is equal to -1, and zeros of x of s. I'm talking only for this example, right? Or s is equal to 1 and s is equal to infinity. So you should also include this 0, which is at s is equal to infinity. Okay. Right. And so we can have zeros at s is equal to infinity. So can we have poles at s equal to infinity? Yes. Right. So we have seen that Laplace transform can have zeros at s is equal to infinity. Particularly when degree of numerator polynomial is less than degree of denominator polynomial. So degree of numerator polynomial is less than degree of denominator polynomial. So in a similar manner, we can show that Laplace transform can have poles at s is equal to infinity. Can you think about it? How? Right? So Laplace transform can have poles at s is equal to infinity simply when the degree of the denominator polynomial is less than the degree of the numerator polynomial. So, right? So as this is a simple thing, I'm not spending enough time on this. Say when degree of numerator polynomial is greater than degree of denominator polynomial, right? So in the sense, you have x of s something like s cube plus 3s square plus something. Here you have s square plus 2s plus something, s square plus 2s plus 10, and here you have s cube. That means the degree of the numerator polynomial is higher than the degree of the denominator polynomial, right? So in such a case, if we take s to be infinity, if we increase s to be infinity, then the value of x of s becomes infinite, right? Because here in the numerator there is s cube term dominating, in the denominator this s square term dominating. So as s keeps increasing, we can neglect the other terms. We can only focus on s cube and s square, and then it becomes effectively s. So as s goes to infinity, x of s goes to infinity. When degree of numerator polynomial is greater than degree of denominator polynomial, limit s goes to infinity, x of s becomes infinity. I'm just erasing this example. This is a very standard calculus fact, right? You must have done it all in your intermediate itself, like in your +2. Yeah. So x of s will have one or more poles at s is equal to infinity when degree of numerator polynomial is greater than degree of denominator polynomial, right? Right? So that means Laplace transform can have poles and zeros at s is equal to infinity. So this is the point I want you to observe, based on the degree of numerator polynomial and based on the degree of the denominator polynomial, right? So yeah, we'll continue I'll take a 2-minute break as always, and then I'll be back. Right. So I'll put my screen. We can as well have multiple zeros. Another thing is we can have multiple zeros or poles. At a particular value of S. Right? So what do we mean by that? So we know that some of the polynomials will have multiple roots at a particular value of S. Say a polynomial, say kind of S plus 2 whole square, right? So it will have no, that's not a good example. So let's see one example here. I have it in notes. So x of t is, so let's find out this. Delta of t minus 4 by 3 e power minus dut minus 4 by 3 e power minus dut plus 1 by 3 e power 2t u of t. So find x of s. So find the Laplace transform. Yeah. So let's see this. So let's divide this into 3 signals. I'm not going to solve the entire problem, but so Laplace transform of delta of t. So let's find the Laplace transform of this first. That is equal to minus infinity to plus infinity delta of t e power minus st dt. Right? So we are simply applying the definition of the Laplace transform. It is minus infinity to plus infinity x of t e power minus st dt. Right? So it comes out to be as this delta function is 1 only at t is equal to 0, it becomes simply 1. Right? Because Dirac delta function assumes the value of 1 only for t equal to 0, and it is 0 at all other values of t. Okay. So now you have Laplace transform is equal to simply 1. What is the region of convergence for this? What do you think is the region of convergence? No matter what is the value of s, right? For at no matter what is the value of s, it is always equal to 1. The Laplace transform of delta of t is always equal to 1, irrespective of the value of s. See, Laplace transform of delta of t is not a function of s. So it converges to 1 for any value of S, right? So what is the ROC? So ROC of Laplace transform of is the entire S plane. So whenever the Laplace transform is not at all a function of S, then whether you put whatever value of S, whether S is equal to 0 or infinity or some value in between, it doesn't matter to that Laplace transform. So it converges for any value of S. So that means the region of convergence is the entire S plane, right? It's the entire S plane. Yeah. Similarly, now let's find the Laplace transform of 4 by 3 e power minus t u of t. This you can make use of our previous these things. 4 by 3, 1 by s plus 1 with the convergence is minus 1. See, this I'm not going to solve in detail. You can see that we have e power minus at u of t. Region of convergence is 1 by s plus 1, sorry, 1 by s plus a, and so on. Similarly, the Laplace transform of 1 by 3 e power 2t u of t is 1 by 3, 1 by s plus 2, and region of convergence is greater than minus 2. Oh, okay. So sorry, I did a mistake here. Here if it is minus t, here it will be plus, and here it is plus, it should be minus here. See, this is the advantage. In a real classroom, you can shout at me that there is a mistake here, but in a remote classroom, yeah, such things. So this is now what is the overall x of s? So overall x of s will be 1 minus 3. So overall x of s will be 1 minus 4 by 3 into 1 by s plus 1 plus 1 by 3 into 1 by s minus 2. So this I'm writing. Okay, so did I make any other mistake? Yeah, so here it is. If it is s minus 2, the region of convergence is greater than 2. So note down the change in this. Okay, it is real of s greater than 2, and it is real of s greater than minus 1. The region of convergences. So this becomes, I'm just directly simplifying it. I'm taking it from my notes. Divided by s plus 1 and s minus 2. And what is the ROC? ROC for this is entire S plane, and ROC for this is real part of S greater than minus 1, and ROC for this is real part of S greater than 2. So this is real part of S greater than 2, this real part of S greater than minus 1, and this is entire S plane. So what will be the final ROC? The intersection of these three regions, right? So intersection of these three regions is what? Okay, so intersection of these three regions is real part of S greater than 2. Fine. Now you see X of S has got two zeros at S is equal to 1. Why? Because both the roots, the numerator polynomial is a degree 2 polynomial. The numerator polynomial is a degree 2 polynomial, S minus 1 whole square. And it has got two roots. Because both the roots of n of S are at S is equal to 1. It's got two zeros at S is equal to 1 because both the roots of n of S are at S is equal to 1. Right? And X of S has got one pole at S is equal to minus 1 and another pole at S is equal to plus 2. So what will be its pole zero diagram? So we have a pole at S is equal to minus 1. So this minus 1, there is a pole. S is equal to plus. So this 2, we have another pole. And at S is equal to 1, this 1, we have got two zeros. So we put two zeros. We call this as a double zero, or two zeros, one pole and another pole. Now let's ask another interesting question. Does X of S in this case has got any zeros or poles at S is equal to infinity? So we said that an X of S can have 0 at S is equal to infinity, or it can have pole at S is equal to infinity. Right? That's what we discussed. What we discussed was, if the degree of the numerator polynomial is higher, it can have a pole at S is equal to infinity. If the degree of the denominator polynomial is higher, it can have a 0 at S is equal to infinity. But here, for this particular X of S, the degree of the numerator polynomial is equivalent to degree of denominator polynomial. Right? So for this, so I'm writing it here. Degree of n of S is equal to degree of denominator of S, denominator polynomial. So it will not have a 0 or a pole at S is equal to infinity. So does X of S in this case has got any zeros or poles at S is equal to infinity? The answer is no. Because degree of numerator polynomial is equal to the degree of denominator polynomial. Right? So whenever you obtain a Laplace transform or whenever you are given a Laplace transform, you should carefully observe the roots and zeros and then plot them in a pole zero diagram if asked. Right? And the pole and another most common mistake students do, at least like when I taught digital signal processing at IIT Varanasi, that in the jet transforms, as I said, there is a region of convergence. So till the end of the course, people start forgetting about mentioning the region of convergence. So some of the students, like, so you should not forget about stating the region of convergence. And if you are asked to plot, if you are asked to give the poles and zeros of the transform, then you should always consider, you should not forget to consider poles and zeros at infinity. So you may simply look at this and then say that yes, you can find the zeros and poles, but sometimes you will miss stating poles and zeros that are there at the infinity. Yeah, and what else? So one final point. Okay, we ran out of pages. So I'll go to the, okay, just I have to erase this entire thing. Like, I'll save this file and then just bear with me for 2 minutes, and then because these 100 pages are over, I have to delete this and then start fresh notebook. I cannot have more than 100 pages in this list. So whatever I'm saving now as a PDF, I'll mail it to your staff members, the JNTU Kakinada staff members, and then they will forward it to you. Yeah, we'll start with yeah, it is done. So let me delete this completely. Yeah. So based on the last example, I just want to give you one homework problem. Find out whether x of t considered in the last example. Has a Fourier transform or not. By examining its Laplace transform. So what I want to do is, in the last example, we have one x of t, and then we found its Laplace transform x of s. Now, based on x of s, I want you to find out whether we can find whether there exists a Fourier transform for x of t or not. Right? So you can do that by simply looking at the region of convergence, of x of s, right? So look at the ROC of x of s, and then decide whether we can find x of j omega or not. So that's a simple reasoning question. It doesn't require you to do any math. It's just when you can have a look at it, think about it 1 minute, or discuss with your friend, and then you can say the answer. Right? Yeah. Now we are moving to the next topic, like next subtopic, properties of ROC. So these properties or some of the characteristics of ROC will help us in understanding the signals in a better sense. Say there is a signal in the time domain x of t, and then we found its Laplace transform, and then we found its region of convergence. Then based on the region of convergence, we can say about the properties of the x of t. Say if you are given only the region of only the x of s, then based on its ROC, you can say something about the time domain signal. Or if you are given a time domain signal, then sometimes even without finding the Laplace transform, you can say about its ROC. So these ROC properties will help you a lot in finding different characteristics of the signals. So we'll start with property 1. Property 1 is ROC of x of s consists of strips parallel to the j omega axis. Yeah. So I'll just note down first, and then we'll discuss. ROC of a Laplace transform x of s consists of strips parallel to the j omega axis, the S plane. Meaning the ROC is always, it is like a vertical strip extending from maybe some value of s is equal to 2 to infinity, or s is equal to minus 2 to infinity, or s is equal to some plus, or it can be between two values of s, but it's always in the shape of a vertical strip. So let's find its justification. Like, so what I'm trying to say is that this is the S plane. So ROC will always be, say for example, this is all ROC. if it is same A, or ROC can be something like this. Say this minus B, and say all this region is ROC, right? Or one more possibility is ROC is in between these two. Right. So it's always like kind of a vertical strip, and then yeah. So deleting this will take a lot of time. So let's do this justification. You can say justification or proof of it, whatever you want to call it. So let's do this on the next page. So let's say what is ROC of X of S. So ROC of X of S is region where X of S converges. So this we can write this as X of t e power minus st dt. Of course, this from minus infinity to plus infinity, and then it's minus infinity to plus infinity X of t e power minus sigma t e power minus j omega t dt. Right? So I simply expressed S as sigma plus j omega. I simply expressed S as sigma plus j omega, and X of S will converge if X of t e power minus sigma t has got, if it converges, or if it has got what you call absolutely integrable. So X of S converges when minus infinity to plus infinity agree? See, this we say that X of S exists when this entire integral is less than infinity. See, if this integral becomes infinity, then we say that X of S does not exist. X of S does not converge. Right? For X of S to converge, this integral has to converge, and for this integral has to converge, we need to have this. So that meaning we need to have this X of t e power minus sigma t dt should be less than infinity. See, because e power in any magnitude of, yeah, so what are we saying here? Let me think. What are we trying to prove? We are trying to prove that the convergence depends only on this sigma. Okay. So okay, and another way of saying this is, if the Fourier transform of X of t e power minus sigma t exists, then the Laplace transform exists. For the Fourier transform of this to exist, it should be absolutely integrable. This value should be absolutely integrable. That means yeah, x of t absolute value of x of t e power minus sigma t dt should be less than infinity. So that meaning the convergence depends only on the sigma. Okay, let's yeah, so the above integral I have to find correct words, otherwise it will be confusing. The integrability of the above integral depends only on sigma but not on omega. Of course, it depends on x of t, but with respect to s, what I am saying is that s is equal to, sorry, so s is equal to sigma plus j omega, and then the absolute integrability of the previous integral depends only on sigma, and it doesn't depend on the value of omega, right? So the ROC is in the form of sigma greater than some sigma 1 or sigma less than some sigma 2 or sigma in between sigma 3 to sigma 4. Only these three are possible. Exist for ROC. That means, as I said, sigma greater than sigma 1. So this will be the ROC, or sigma less than some sigma 2. Maybe this is sigma 2. So this will be the ROC, or sigma in between sigma 2 and sigma 3, sigma 3 and sigma 4, sigma 3 and sigma 4. So this will be the ROC. So as the ROC depends only on the real part of S, see, all this discussion can be simply stated in two sentences, like as the ROC of x of s depends only on the real part of S, it will always be in the form of vertical strips. ROC of x of s depends only on the real part of S. The ROC will always be the form of vertical strips. Right. So what I observe is we need not even have so much discussion for this, because while introducing the concept of region of convergence, what we found was it depends only on real part of S. Then we can as well take that discussion here and then observe that as the region of convergence depends only on the real part of S, and our ROC is indicated on the S plane, where x-axis is the real part of S and y-axis is the imaginary part of S. We can state that the ROC depends only on the real part of S, which means that the ROC will always be in the form of vertical strips. Say for example, when you go to jet transform, you will see that the ROC is always in the form of a ring, is always in the form of a concentric circles, or it's like a stripe. It's a circular stripe. Here it's a vertical stripe, but whereas in jet transforms, it is a circular patch or circular stripe, if I can call it so. Right. Yeah. So and I'll state property 2, and then I'll stop it there. We'll continue in the next class. Property 2. For rational Laplace transforms, ROC does not contain any poles. Yeah, do we need a justification for this property? It's obvious, right? It's very intuitive that by definition, what is the region of convergence? The region of convergence is that region in S plane in which x of S converges to a finite value. So whenever there is a pole, x of S will have a value of infinity. X of S will diverge to infinite value. So that meaning we cannot have poles in the region of convergence. It's because at a pole, x of S becomes infinity. And we'll have property 3. If x of t is of finite duration and is absolutely absolutely integrable. See, if x of t satisfies both these conditions, that x of t is a finite duration signal, it doesn't extend up to infinity, it exists only for a finite duration, say from t1 to t2, and if it is absolutely integrable, then its ROC is the entire S plane. So its ROC is the entire S plane, right? So this property we will prove in the next class, and then there are, I think, 7 or 8 properties. We'll finish all the properties in the next class, and then we can move on to inverse Laplace transforms.